Hello and welcome. So in this video lecture, we are going to continue our discussion on the generic components of reasoning with description logic. Right. In the last video lecture, we have discussed different tasks relevant to the A-box reasoning. And here, particularly, we'll be talking about different examples of such reasoning in A-boxes, with A-boxes. And the specific focus or specific interest would be on how really this open world assumption is related to the A-box reasoning. So these are the two things we will be doing in this video lecture, right? So the first task that we have discussed for the A-box reasoning task is the consistency checking task, right? So what we basically mean by consistency checking task? So we have one T box. So we are dealing with consistency checking task. Consistency checking, and these are all related to A box reasoning. So whatever we are discussing here is related to A box reasoning, right? So under consistency checking, so let us talk about one. So what we have, we are given with a T box and one A box, right? So what we need to say, whether this A box is consistent with respect to the T box T or not, right? So basically, how do we really do that? So we say that this A box is consistent if there is an interpretation which is the model of both this T box and the A box. So you got to find at least one interpretation which is a kind of model of this T box, and also this interpretation is a model of this A box, right? Now let us try to take some concrete examples. So let us consider our T box to contain only one T box axiom. So our T box is something like this, which we have already discussed in the last video lecture. So the T box contains one statement which is kind of doctor, and doctor concept is equivalent to human intersection, not of animal, and something that has treated at least one thing, right? So this was the kind of this is the kind of T box axiom that we have inside our T box, right? Now let us consider two A boxes. So one is Dr. Ravi, and we have something like, say, Ravi is a human, and Ravi has treated, say, Tom, and say we have another fact which is like uh, Rahul has treated here, right? So this is one A box. So this is A box 1. We have got another A box which is A box 2, and it contains the assertions like, say, Dr. Ravi and animal Ravi. Then we have has treated say Ravi, Tom, and has treated Rahul here. So if we just look at this A box A1, this A box A1, and try to see whether this is consistent with this T box or not. So you see that Ravi is a doctor, right? And Ravi is also human, and not animals means Ravi will be a member of not animal, and Ravi has treated at least someone. So this particular A box is really a consistent A box with respect to this T box, right? Now let us focus on this A box, right? Now we are making Ravi to be a member of doctor, right? Now at the same time we are making Ravi to be the member of animal. Now according to the definition of doctor, doctor is someone who is human and also belongs to a class which is a complement of animal but not animal, right? So that's why we are having an inconsistency. You cannot have any interpretation. So you cannot have any interpretation for which both T and A2 can be satisfied, right? But for A1, we can have at least one interpretation, which is a model of T for which this T will be satisfied as well as A1 will be satisfied. So in that case, A1 is consistent, but A2 is not consistent, right? So this is how this is a kind of demonstration of what we mean by consistency checking, right? Now let us move to the other A box reasoning task, which is instance checking. Instance checking. And what do we mean by that? So again, we will be given with an A box, right, and a T box, right, and we need to say whether A box entails some membership of one instance into a class with respect to the T box, right? So what we are trying to see whether A is an instance of the class C given an A box A, right? And that you have to do with respect to T, and that is what we call as instance checking. So this instance checking is at the concept level, but if you see want to check an instance in the relation level, so this is what the form would be. So you need to check whether AB is related to R, related with R in and that goes with the A box and the T box, right? So let us take an example of such a case, right? So let us assume that our T box contain a different inclusion, the class inclusion axiom. So what are the class inclusion axioms we have? So let's say we have something called there exists teaches course. So someone teaches a course, that means either that thing is a student and also has got at least one degree, which is master's, right? Or the person or the entity is a member of professor class, right? So someone who is teaching a course either may be a professor or a kind of student teaching assistant. So this part is modeling the teaching assistant and this part is modeling the teacher, right? Now prof is something, or prof is a subclass of the class of the individual that has got at least one PhD degree, right? And if someone has got a PhD degree, then he or she has also got an MS degree, right? And finally, we say that this PhD and MS, they are disjoint classes. So they are disjoint with each other. So we need to say that the intersection of PhD and MS is a subclass of the bottom class, right? So this is our T box. Now what is our A box? Now this A box contains different assertions. And what are the assertions? So we say John teaches chemistry, right? Teaches chemistry. So John is a member of the class of the individual that teaches at least one course. So chemistry, right? And John has got at most 1 degree. John has got at most 1 degree, right? And chemistry is a course, is a member of, oh, sorry, chemistry is a member of course, right? So from these two, we want to check whether John belongs to the class student. So what we are trying to check, that A entails the fact, A entails the fact that John is a student. And with respect to the T box T. So either it will be true or false, right? So from this we need to prove whether this is true or not. And this is what we call as the instance checking problem. So it is an example of the instance checking problem. So this very problem will be solving while we will be talking about the different problems related to description logic in the subsequent video lectures. So you are living with just the problem description. We will be solving the problem later, right? Now the third problem that we have discussed and that is related to A box reasoning is the instance realization. Instance realization, right? So here from the T box and the A box, we need to infer the most specific class of a particular entity or individual. So that is the kind of problem that we have in our hand, right? So to illustrate this problem, so let us assume the T box to be say the same thing. Doctor is equivalent to human and not of animal and has treated at least one thing, right? Now let us assume our A box to contain something like say Ravi is a doctor. Ravi is a doctor and Ravi has treated Tom. Ravi has treated Tom, and finally has treated the Rahul Kiara. Right. Now, if we try to see that can we have other classification of Ravi, right? So from this definition, from A and T, we can say that Ravi is a member of the human class, right? Because something that is a doctor, that is also a human, right? Now from this two definitions, you cannot really say whether Rahul is a doctor, right? Rahul is a human or not, right? So we cannot really say that Rahul belongs to human. So we cannot say at this point of time, right? Now let us assert something else. So let us now add this particular thing in our T box. So our revised T box, T prime, so let us take this to be say T1 is equal to T1. We have T1 as it was earlier. Then we assert that if someone has treated at least one, then that thing is a member of human, right? Now if you have added this to the T box, now you can classify Rahul to belong to the human class, right? So with this, let us now move on to the relationship between the open world assumption and a box reasoning, right? So open world assumption and a box reasoning. So let us to illustrate this relationship, let us consider one a box which we have already talked about, the same a box. So a box contains three assertions, that is Ravi is a doctor. Then we have has treated Ravi Tom, and has treated Rahul here. So the same thing, right? Now, one thing that is pretty relevant to discuss here, that these A boxes, they have a very close relationship with the relational database, right? So whenever you are trying to model or represent information or knowledge about a particular domain, so the in earlier settings or earlier scenarios or even now, people generally make use of relational databases, and the relational databases, they are basically containing different relations, and these relations, they are represented by tables, right? And you can easily see that these A boxes, they can be translated into tabular form, that is that is a kind of modeling paradigm in the relational database, right? So let us see how we can convert this into relational databases, and why we are doing that really. So the motivation for which we are doing this is exactly the case, due to the case that relational database, they follow a closed world assumption as compared to the open world assumption that is followed in the description logic or semantic web in general, right? So that's why you are trying to draw a parallel comparison between this relational database way of processing the thing and description logic way of processing the thing, right? So now let us convert this into a relational database form. So we are converting this into a relational DB form, right? So let us try to see how we can just represent this in a tabular form, right? So what we can do, we can create a table called doctor. So this is a table, and this table will contain one row which is Ravi, and this says that Ravi is a doctor, right? And similarly, we can create another table which is called has treated, and this has treated table will be having two columns. So the first column would be the kind of a person who is treating, and the second column will be having the reference to the person or the entity who is which is being treated, right? So if we just translate this into the record form, then we have Ravi to be the first entry in this column, and Tom will be the entry in the second column for this first record. And for the second record, we can just say Rahul has treated Kiara. Right. Now let us try to query something from this relational database. So what we are trying to query? We are trying to see the instances. We are trying to find out the instances or individuals that have treated at least one thing, right? So if we just put a query like this here, so the answer that we'll be getting is basically two answers we'll be getting. One is Ravi and other is Rahul, right? So, and if you try to do this, put the same query in the A box system, we'll be getting the same set of results, right? So the point that will be kind of very relevant here, that the this DLA boxes, the DLA boxes, they can be easily translated into relational database form. However, though they are kind of the representation is kind of interchangeable. You can represent something that you have represented in a box into a relational database, and something you have represented in relational database, you can convert that easily to a DLA box. But they differ in the way they are processed. Basically, they differ in the semantics. So they differ in semantics or interpretation. Semantics or the way they are interpreted. Right. Now, the difference lies in the fact that A box follows open world assumption and the relational DB follows closed world assumption. Right. So what is the kind of implication that we have in reasoning if A box follows OWA and relational database follows CWA? So for the case of A box, I'm talking about this case. If you have something like this, that A box A entails a fact alpha, then we say that alpha is a consequence of A. So that means if A is held true, then alpha is also held true, right? Now, the other case where say A box A does not entail alpha, right? So this will always be with respect to a T box. I'm omitting this T box for the sake of simplicity, right? Now this, if we say that this A box does not entail, so I'm putting a kind of cross to mean that this A box does not entail alpha. So it does not imply that the negation of alpha holds. We cannot really say that if we follow OWA. So whenever you see that alpha is a consequence, alpha is modeled by A, then we entail by A or A box A, then you say that whenever A is true, then alpha is true, right? Now if you say that if A does not model alpha, so alpha is not a consequence of the A box A, so that does not mean that the negation of alpha holds, and that goes with open world assumption. But in closed world assumption, in the case of relational database, uh, so that this case here, if we have something, so this case will this when A entails alpha, this case will always be the same for A box way of reasoning and relational database way of reasoning. But for the case of where alpha is not entailed by A, there the relational database will differ the kind of thing it can infer. So what will be inferred using this relational DB way of representation? So here we will be inferring that negation of alpha holds, and that goes with the case of closed world assumption, right? So when we say that alpha is not entailed by the A box A, then we assume this alpha is false. So this negation of alpha holds. That means alpha is false. But in open world assumption, we do not say that this not alpha is true or this alpha is false. We cannot say that for sure, right? So that is the basic difference that we have when we process something in a description logic way, or we process the same thing in relational DB way, right? Now, if we go back to the example that we have started with, this example. So here, you see Rohit does not appear. Let me write it down properly. This is Rahul. So you see Rohit does not appear in the in the first column of any of these rows, right? Now, so that is the case that we observe, right? So Rohit does not appear in the first column of any of the rows in the hash treated table, right? So if we put a query like this in this particular situation, that for all hash treated not, so that means uh, something that has not treated anything, right? The thing or the individuals that have not treated anything, right? So I'm trying to put a query like whether Rohit is a member of this class or this concept expression, right? So as per CWA, we say that Rohit is a member of, so this particular thing. So if we say that this is my C, this is a kind of concept expression C, we say that this concept expression C, Rohit, so basically this is my alpha, right? So this is the alpha that we are kind of asking, right? So Rohit will become true, right? We are saying that Rohit has not treated anything. That becomes true under CWA, right? Now, if we go with OWA, we cannot say that the C Rohit is a consequence of the A box A. So we cannot say that. So is not true. We just say is not a consequence. That would be the best thing. Is not a consequence of A. Right. So that is the difference that we have. So the other case, if we put another query that Rohit, whether Rohit has treated at least one thing, right? So how do we represent this in description logic? We just say that greater than equal to 1 has treated top Rohit. This will become a false. This becomes false in both CWA and OWA. So this is the kind of difference we have. Right. Now, as far as the membership of one individual in a class is concerned, there are basically three possible outcomes. So, three possible outcomes of the membership question CWA. Right. The first outcome is that A belongs to C in all the models. A belongs to C in all the models. The second case is A belongs to C, not C, in all models. And the third case is basically neither 1 nor 2 holes. So basically you are saying that the fact that A belongs to C, the state of the fact of A belongs to C is unknown. We do not know this. So these are the three possible outcomes we can have. We know for sure that A is a member of C, where we say that this A belongs to C will happen for all the models, and we can say for surety that A does not belong to C if A belongs to not of C in all the models. If both of these does not hold, so neither 1 nor 2 holds, then we say that the state of A belongs to C is unknown. So that is what we do in the open world assumption. So whatever we know for sure, we represent that like A belongs to C or A does not belong to C. Does not belong to C. But if we cannot say for sure that A belongs to C for all the models or A does not belong to C in all the models, then we cannot really say for sure whether A belongs to C or A does not belong to C. So that is the kind of, we have an unknown state, unknown truth there, right? So let us try to take another example and try to illustrate the concept more. So our revised representation is, we have the table has treated and here we are having only one rule, Ravi and Tom. And we are saying that Tom is belonging to the animal class, and it is a kind of relational database way to write the thing like, say, animal Tom and has treated Ravi Tom. Right. So this is the description logic way to say the thing that we have stated in the relational database way. Right. Now let us ask a query. The query is whether Ravi is a member of the class, which is the kind of class of all the individuals who have treated only animal, right? Whether, the question that we are trying to ask, whether Ravi has treated only animals, right? So the description logic way of say this thing is, for all has treated animal. So this is the class expression, which means that things that have treated only animals, right? And we are trying to see whether Ravi is a member of this class. So this is the kind of query that we have, right? Now, if we go by CWA, this will become true because Ravi has treated Tom, and Ravi has treated only one thing as per the relational database, and Tom is a kind of animal, right? So in CWA, we'll be having the answer to be true for this particular question, right? But for OWA, we cannot conclude anything. So we cannot conclude this, cannot conclude the truth value. Why? Because there might be another model where Ravi has treated someone. We might be having another model where Ravi has treated something else which is not an animal. So in that case, I cannot say Ravi has treated only animal, right? To ensure that, we need to assert. So to ensure that this will become true under OWA, we need to assert the fact that Ravi has treated at most one thing, right? And the description logic way of saying this is, Ravi is a member of the class uh, of things that have treated at most one thing, and make Ravi to be member of this, right? So this is what we call as the closure axiom, which we have talked about earlier. So we are adding something else to this. So we know this thing, but also you are saying that Ravi has treated at most one, right? So we cannot have another relation here where Ravi has treated something and which is belonging to a class which is something different than modern animal, right? So that's why this will then return the truth value of this query to be true, that Ravi has treated only animals, not other things, right? Now let us take another case, a very interesting case, to illustrate the idea of reasoning with a box statements more, right? And that case is the case of Oedipus, right? So the case of Oedipus is a character from the Greek mythology, a kind of tragic story where Oedipus was born to Iocasta and Laius. And Laius was the king of Thebes, right? and there was a kind of prophecy that uh, the child was born to the Iocaста and Laios would kill the king, right? And then Oedipus was kind of uh, asked to be killed, but finally he was not killed. Then he came back and killed the king and married his mother, right? Now the story goes along, so there are many other facets of the story, but we at this point of with the description we can really talk about the kind of example that we are talking about, right? So what we know about this part of this particular story, so we have one individual, Iocasta. The other individual is Oedipus, uh, Polykinesis, kinase, Polynikes. Then we have uh, Tharsandros. Now, Iocasta has child Oedipus. Oedipus. Right. So I'm not writing has child, I'm just writing H. And Iocasta has child Polynikes. And Oedipus has child Polynikes. And Polynikes has got child Tharsandros. Right. And what we know else, that Oedipus is a patricide who has killed his or her father, right? So patricide is the class of the thing where the members they have killed their father, right? And we know for sure that Oedipus is a patricide, and we know for sure that Tharsandros is not a patricide, right? And we do not know whether Iocasta or Polykinase, they belong to either of these two classes, this patricide or not patricide. We do not know this, right? So we can easily convert this into the relational database form. So this is our A, right? And what would be our relational database form? We'll be having one table where we just say that Oedipus is a patricide, right? And Tharsanders will belong to not patricide because of the very fact something that is not stated in relational database, that will be assumed to be false, right? So we'll say that Tharsanders does not belong to the patricide class. That will be the kind of uh, mm, closed world assumption way of thinking, right? Now the other relationship, which is kind of has child table, it contains multiple records, right? So the first record is Iocasta has child Oedipus. The second record that is true is Iocasta has child Polynicus. And finally, Oedipus has child Polynicus. And the last record in this table is Polynicus has child third son does. Third son grows. Right? So this is what we know to be true, and this is kind of relational database way to represent this A box. Right? Now the question that we want to ask is, does Iocasta have a child who is patricide and who in turn has a child who is not a patricide? Right? So what we are trying to query, so let me trace this query in the next slide. So we are trying to see whether our A box models that Iocasta is a member of a class. And what is that class? That class is that Iocasta has a child and the child is a patricide and has got a child that is not a patricide, right? And we want that Iocasta, and we want to ask whether Iocasta is a member of this particular class, right? So if we assume this to be C, so we are trying to see whether A entails alpha where or alpha is C Iocasta. So this is what we are going to ask, right? Now let us go with the relational database or the closed world assumption, right? Now what would be the answer with closed world assumption way? So let us go back the graph, right? So here Iocasta has one child which is ODPS, and ODPS is patricide, and Oedipus has a child polykinase, and we have not any entry regarding this polykinase, whether this polykinase is a patricide or not. Now as something that is not stated in the database, that is assumed to be false, then we will assume that this polykinase does not belong to patricide as per CWA, right? Now what we have, Iocasta has got one patricide child, and this patricide child, which is Oedipus, has got a child that is not patricide. So we'll return true. So the CWA will return true because of the fact that Oedipus is a patricide and has a child in the form of polynicus who is not patricide, right? Now let us think what would be our DL or OWA representation, inference or reasoning, right? So let us consider a reasoning path. Let us name this to be reasoning path 1. We will be having multiple types of reasoning. So let us name this to be reasoning path 1. So here let us first check this whether this is true or not. Whether let us see whether Iocasta has a child Oedipus. This is of course true, right? Now, Oedipus is patricide, right? But Polynicus is not known to be patricide. So you have a question mark. If you go back, we have a question mark here. So we do not know for sure whether Polynicus is a patricide or not a patricide, right? So if as we have got uncertainty, so this this path. So if we follow this path, Iocasta to Oedipus and this Oedipus to Polynicus is becoming to be false. So we discard this Oedipus to be a contender. So we discard this. Oedipus case is discarded. Right. Now, Iocasta has got another child. Has child Polynicus. So you see, we have got Iocasta has got one child Polynicus, right? Now, Polynicus has child Sandros, who is not a patricide, but we are not sure. Uh, mm, we are not sure whether Polynicus is a patricide or not. Right. So in that case, we this Polynicus path, this is also ruled out. So this path of reasoning is also ruled out. So Polynicus is ruled out. So you see, we are left with no option. So through this path, we do not have any the answer to be true, and through this path, the answer also is kind of false. So here we can say that this A does not model C Iocasta or entail Iocasta. So this is what we infer, right? But there is a kind of catch here. If you see that this Oedipus is patricide, but the Polynicus is not known to be patricide. So this is kind of uncertain. So this state is really unknown. And here also this, if you look at Polynicus, we are not really sure whether he is patricide or not. So here we have also got a kind of unknown state. So the fact that we are deriving that Iocasta is not a member of this particular class is a kind of vague. So we cannot really say for sure that this is kind of becoming to be false. So we cannot really say that. So let us look at another path of reasoning. So we are looking at reasoning path 2. So here what we will be doing, we will be taking a very methodological approach, right? So here we see that there are two nodes in this graph which are marked to be question mark, right? So we assume that we have for any individual it may either belong to patricide or not belong to patricide, and that is a valid assumption, right? So the first thing that we are assuming that an individual is either a patricide or not a patricide. So if you take any individual A, it either belongs to patricide, it either belongs to patricide or A belongs to, does not belong to patricide, right? So we'll be considering those interpretations where A is either belong to patricide or A does not belong to patricide, right? Now let us consider our first interpretation or first model, right? So our model 1, in model 1, let us take it to be, say, gamma 1, right? So here we assume that polynicus is a member of patricide. So here this patricide to the power gamma 1 is basically the set of individuals that belong to this patricide, right? And we assume that this polynicus belong to this particular patricide class, right? Now if we assume that, so what will happen? So Iocaста has child Oedipus, which is a patricide, and Oedipus has child Polynicus. And Polynicus, we have assumed this in this model to belong to patricide, right? So by this path, this is becoming false, right? But we have got another path. Now this Iocaста has child Polynicus, and Polynicus is a patricide, right? Now this Polynicus has child Tharsandros, and Tharsandros is not a patricide, which is explicitly stated, right? So we have one path, at least one path by which we can satisfy the concept expression, which is not there exists has child patricide and there exists has child not patricide. So and that path is really this path, right? So we say that through this interpretation, A models C Iocaста, right? Now if we want to make this to be true, C Iocaста, if we want to make this to be true, then we need to check whether this is true in any interpretation, any given model of A, right? And we have established that this C Iocaста is entailed by A under model gamma 1, right? Now let us consider model 2. Model 2. And there we are considering the model to be gamma 2, right? And there we consider the other path of the reasoning. So in one path of the reasoning, we have considered that A is a member of patricide and we will be considering these cases, and we don't have any other cases, right? Either this is true or this is true, right? And through this path we have already established that A entails the fact that C Iocasta is a member of this class, or this class C, right? Now let us consider the other part. So we say that Polynicus is not a member of, or the other way of saying this, is a member of the negation of patricide, right? Now if this is so, then we have got Iocasta has child Oedipus, who is a patricide, and Oedipus has child Polynicus. And Polynicus we have assumed in this model to belong to not patricide. So what we have? We have the fact that Iocasta has got at least one child who is a patricide, and that child has got at least one child which is Polynicus, that is not a member of patricide. So you see we are satisfying this particular class expression, and here also you can say that A models or A entails the fact that Iocasta uh, belongs to the this class expression C, right? And this is under model gamma 2. So basically either this is true or this is true, right? And either of this model derives the fact that Iocasta is a member of C. Iocasta is a member of C. So that's why you can say that uh, this A models alpha, where alpha is basically C Iocasta, is true under any given model. So this is how we realize, or we understand the consequence of open dual assumption in the A box reasoning. So with this we end the portion of the generic part of the reasoning with description logic, and in the next set of video lectures we start talking about different problems related to description logic representation as well as reasoning with description logic in general. Thank you very much.